I have a gold tooth. Hey guys, hi Kevin. Oh, can't hear me yet. Hi Gabe. Hi Kevin.
Hello.
Hello.
You know something? Actually, Gabe, you've been on the discussion. I've seen it. You've been on the student talk portion of it. Keep on using it, God.
Okay.
You can trust Aubrey and Jessica to give you fairly good answers. All right.
Okay. Yes.
Yeah, this is, God, literally speaking, this is what it was intended for. And this is why I'm making it a pain for you guys to have to respond. By the way, Jasmine is good too. She's about to come in here. We doing okay, guys?
Yes.
Yep. How about yourself?
Peachy keen, wonderful. I'm vacuuming the house even as we speak. It's great having a Roomba. Now, if I only had a cat to put on it. You ever seen that? The video of the cat on the Roomba?
My cats don't like it.
But who says they have to enjoy it? I'm sure you could probably super glue the cat to it somehow. What do you think?
I don't know about that.
I've seen cats riding them.
Yeah, that's what I'm talking about, Cassidy. That was Cassidy, was it? Or was it just Mina?
It was Dylan.
Sorry. I'm horrible at discerning voices. Jasmina, you're doing a good job answering the questions. I've seen a couple of them.
Thank you.
In the forum. Very good. Okay, guys. We're going to, I got to do some molecular weight calculations first, which is going to be really nothing. I have a system that I like to use for that. And guys, I don't care if you use any system. This just seems to work for me. So I'm going to quickly show it to you and we'll be done with it, okay? Now all I got to do is find the silly thing. There it is. All right, we're seeing the screen, aren't we? Guys, we're seeing the screen?
Yes.
Yes.
Okay, basically, if you got a simple molecule, then don't even bother with this because it doesn't make any sense. If you have something like sodium chloride, you know you have one atom of each. Just look up the atomic weight of sodium, 22.99. Look up the atomic weight of chlorine, which is 35.45, and just add them together. So this doesn't make sense for simple molecules. However, if you have a more complicated molecule, sometimes doing it this way just kind of organizes it for you, and you know you have the right answer at the end. So basically, what you're going to do, you're going to list the type of the elements in the compound. Beside that, you're going to look at the subscripts, and you're going to put the number for each atom. Beside that, you're going to put the atomic weight of that particular atom. Then you multiply the number by the atomic weight, you get that element's contribution. Add up all the contributions, you end up with the molecular weight. Now, which atomic weights do you use? Find the periodic table. I'm sure you're going to find different weights on it. Basically, what you have to do is you have to look at your data. I don't want a new slide. I wanted to bother the old one. Cut. Okay. Say, for example, you have 36 grams of carbon dioxide. Okay. Would it be okay to use 12 grams for carbon and 16 grams for oxygen? Would that be okay? What do you think,
Yes.
Gabe? Would that be okay?
Yes.
Because look, this is what you're starting with. You're starting with something that's two significant figures. By using atomic weights that also have two significant figures, you are not limiting the number of significant figures in your final answer. On the other hand, if I had 36.45 grams of CO2, can I use 12 grams of carbon? Because if I use 12 grams of carbon, that means I am going to limit the sig figs of my carbon dioxide from 4 down to 2. Does that kind of make sense, guys? Am I making sense here, guys?
Yeah.
Okay. All right. So when I'm doing my chart, so that's a strategy on which atomic weights to use. If I'm dealing with aluminum sulfate, Al. Ugh. Yeah. Jesus, I lost my head there for a second. Aluminum sulfate, Al2 parentheses SO4 taken 3 times. So I look at my elements. I've got aluminum, sulfur, and oxygen in there. For my aluminum, my compound is Al2 SO4 taken 3 times. All right. My subscript on my aluminum is 2. I put 2 as a number. My subscript for my sulfur is 1 times 3. I got 3 sulfurs. My oxygen is 4 times 3 for 12 oxygens. I simply multiply that by the atomic weight. This gives me aluminum's contribution. The 3 times 32.06 is sulfur's contribution. The 12 times 16 gives me oxygen's contribution. To get the molecular weight, all I do is add the 3 up. Make sense, guys?
Yes.
Do I need to go into this further? Do I need to give other examples, or are we pretty much on target with this?
I think I've got it.
Is everybody okay with this? If anybody wants another example, please, I'll be happy to do it. I just think this is a fairly simple concept that we can go through with it by just the way it is. We good?
Yeah.
All right. Having done that, we are going to get into empirical formula problems. Are we seeing the purple screen now?
Yep.
All right. I've kind of broken these down into different types of problems, and I'll go through each one before the end of the day. A type of an empirical formula problem is a percent composition from given weights. You can get the percent composition from the empirical formula. You can actually do the empirical formula calculation from weights. You can get that empirical calculation from reacted compounds. You can get it from percent composition. And the last thing we're going to do is we're going to turn molecular formula calculations from empirical formulas and molecular weights. So again, just as a little reminder, a molecular formula is a formula that defines the exact number of atoms that are within that compound. If I have glucose, that is C6H12O6. I have to have 12 atoms of hydrogen, 6 atoms of oxygen, and 6 atoms of carbon in order to make a glucose molecule. But I can also express this in something called the empirical formula, which is the smallest ratio of atoms present in the molecule. So if I have C6H12O6, can't I divide each of those numbers by 6?
Yes.
You see, this is where I pause and you answer, you scream out yes, okay? That's how this works. By the way, Jessica, you out there, Jessica? Jessica.
Yes. Yes.
I'm giving you a compliment now. Good job on answering in the forum. Jessica's another person you can trust for answers.
Oh, I don't think that was me.
You don't think that was you? Okay, then don't trust Jessica. Okay, so if I have C6H12O6, the empirical formula would, if I divide all those subscripts by 6, I get CH2O. Nothing, you guys, I've gone over this before. Now, if I look at a compound, if I look at a molecule, if I'm looking at iron 2 chlorate, iron 2 chlorate, each atom or each molecule of iron 2 chlorate has 1 atom of iron, 2 atoms of chlorine, and 6 atoms of oxygen. Is that fair enough, guys? Do we agree
Yeah.
with that?
Yes.
Okay. What if I was to multiply that, each one of those, by 6.02 times 10 to the 23rd? Would I still have the same ratio of 1 to 2 to 6?
Yes.
So if instead of having 1 molecule of FeCl3 taken twice, if I have 1 mole of it, then don't I have 1 mole of iron, 2 moles of chlorine, and 6 moles of oxygen? The
Yes.
subscripts, in other words, determine the molar ratio of the elements within the compound. Are we good with that, guys?
Yes.
Guys, this is why, remember I told you, don't carry over the subscripts. If you are reacting barium chloride with sodium hydroxide, it is not NaCl2 because you have changed the molar ratio of chlorine to sodium. So don't do that. This is just another aside. All right, let's get into the actual problems. Does anybody know what percent means? Percent.
Out of 100.
Out of 100 per century. That's why it's been shortened down. So basically, all you're doing is taking the part divided by the whole. Then in effect, what you are doing when you divide the part by the whole, you've got the part per 1. Does that make sense to you?
Yes.
Yes.
So if you've got the part by 1, in order to get the part per 100, you have to multiply the numerator and denominator by 100 over 100. In effect, so you're saying a percent. What you are doing is you're taking the part divided by the whole and you're multiplying that by 100. That makes sense to you?
Yes.
Thank you. So if I'm dealing with batting averages, if I want to know the percent times that a batter gets a hit, what I have to do is I have to take the number of hits and I have to divide that by the total number of times he got up to the plate. Because if you got a hit, you had to be up at the plate. So that is the part. The whole is the whole number of at-bats. So if a batter gets 99 hits every 300 at-bats, basically we're dealing with a success rate of 33% because I'm taking the 99 hits dividing it by 300. That gets me 0.33 divided by 1. I multiply numerator and denominator by 100, and I get 33 per 100. So if I react 11.7 grams of iron with 4.8 grams of oxygen, I want to know the part of percentage of iron. So my part is going to be the grams of iron, the 11.17. But the whole is going to be the 11.17 plus the 4.80. So all I got to do is take my 11.17 divided by 15.97, and I have my answer. Multiply it by 100, I have my answer. Simple enough, guys?
Yes.
Thank you, my designated yes person. All right, so that's simple. If I have given weights, all I got to do is take the part I'm interested in, and I got to add all the weights of all the other things to that, and I take the part I'm interested in and divide it by the whole. I have my answer. Simple enough. Now, what is the percent of iron in iron sulfate? We got to remember a couple things. One of which is that I can get the weights from the atomic weight. And if I get the weights from the atomic weight and divide the atomic weight by the molecular weight, I'm going to come up with a percentage. And since the ratios do not change in any of these, it does not change, or else I don't have iron 2 sulfate. As long as that doesn't change, then my percentages are not going to change. So all I got to do here is I got to find the atomic weight of iron, divide that by the molecular weight of the iron 2 sulfate, and I have my answer. My molecular weight of iron 2 sulfate is 151.91. Iron is 55.85. I divide that by the 151.91. I get my percentage. All right. The cool thing about this is, as long as you have a formula and as long as you have a weight, you can tell how many grams of which atom you have. Are we good with that?
Yep.
Yeah.
Now I'm going to get into the lab. Okay? You can calculate a percent of a portion of a molecule. All you have to do is add up what the portion weighs and divide that by what the whole thing weighs. A hydrate is a compound, is an ionic salt in which the water has been absorbed into the crystalline matrix of the salt. So literally speaking, it becomes part of the weight. So sometimes we need to figure out what that percent is. So if I have a compound, BaCl2.2H2O, and I want to know the percent of water in that, all I have to do is figure out how much water contributes and divide that by the weight of the whole thing. I have 2 waters. Each water has 2 hydrogens, 2 times 1.01, and 1 oxygen, 1 times 16, or 18.02. But remember, in my formula, I had 2 of them. So I have to take the 18.02 and multiply it by 2 so that water's contribution to BaCl2.2H2Os is 36.04. Now what I have to do is I have to get the weight of the barium chloride. Barium chloride weighs 208.23. I add this to the amount of water. my whole weight of BaCl2.2H2O weighs 244.27. I simply am going to take the weight from the water, divide it by the total weight, and that will give me the percentage. Questions? Could I figure out the percentage of chlorine in the compound? If I have BaCl2.2H2Os, can I figure out the percentage of chlorine in my compound?
Yes.
All I'd have to do is take 2 chlorines, 2 times 35.45, which is 70.90, and divide the 70.90 by the weight of the whole thing, the 244.27, and I will get the weight of chlorine. If I have a polyatomic, if I need to know how much percentage of the ion is present, I can still do it. Okay, now we're going to get into the empirical formula. All right, guys, remember when I told you that the subscripts were the simplest molar ratio of the atoms? That's all subscripts are. It's the molar ratio of the atoms within that molecule. So basically, the strategy that's going to work is that we are going to turn our weights into moles. It's the first step. Then we are going to divide the moles of each type of atom by the one that's the smallest. That will give us the molar ratio. And that is what we're going to use to apply to the individual elements within a molecule. That is, if after you divide the smallest number of moles, if it is a whole number. If it's not a whole number, then we got to do a little manipulating. So, yep. Has anybody ever seen a chemical formula with a fraction of an atom as a subscript?
No.
You can't add a half an atom of oxygen. So you have to make sure that all of the subscripts are integers or whole numbers. Now, in intro, did your professor make you memorize the chart? If the answer ends in 0.33, you multiply by 3. If it ends in 0.25, you multiply by 4. If it ends in 0.5, you multiply by 2. Did they make you memorize that chart?
They did, but I have completely forgotten it, honestly.
You don't have to memorize it. You don't have to memorize that chart. What you do, multiply the decimal value of after you've divided the smallest weight into the smallest number of moles into the others. If you end up with a fraction, start with 2. Multiply your fraction mole by 2. If that gives you a whole number, you're done. If it doesn't give you a whole number, do 3. If that doesn't give you a whole number, try 4. That doesn't work, 5. Guys, by the time you get to 10, I would consider re-looking at your problem because you probably made a mistake. Okay? So, actually, if you go beyond 5, you've probably made a mistake.
You could also just divide it from 1, and then you'll get the number you get to multiply to get it to a whole number.
Okay. Good enough, Gavin. That works as well. As I said, I don't care if you use my system. I don't care about that. What I care about is that the system you use works, and that will work, Gavin. Does everybody understand what Gavin said? Basically, what he's saying is you take 1 and you use the fraction part. So if it's 0.25, you divide the 1 by 0.25, you end up with 4. That's actually very good, Gavin. Can I steal it?
Yes, because it's just math. It's not really mine.
Okay. I have a compound that has 4.151 grams of aluminum and 3.692 grams of oxygen. Determine the empirical formula. Okay? First step, when you're doing any empirical formula problem, you have to get the weights. Weights are given to us, so step one's done. Second step, turn the weights into moles. So I'm going to take the 4.151 grams of aluminum, I divide it by 26.98, I get 0.1539 grams of moles of aluminum. I now have 3.692 grams of oxygen. I divide that by, guys, do I use 16 or do I use 32? I'm trying to find the moles of oxygen. Do I I multiply the grams by 1 mole over 16, or do I multiply it by 1 mole over 32? What do you think, guys?
16?
16? You don't sound very sure.
I haven't had enough coffee yet.
Cassidy, if it's 16, why would you multiply it by 16?
Because is that the molecular weight of oxygen?
No, it's the atomic weight of oxygen.
Atomic, oh. Well, because of that.
Exactly.
Okay.
What are you trying to get the molar ratio of? Are you trying to get the molar ratio of the oxygen atoms? Or are you trying to get the molar ratio of the oxygen molecules? When you do empirical formulas, when you're faced with a diatomic molecule, empirical formulas use atomic weights. Later on, the next subject we're going to get into is stoichiometry. In stoichiometry, you want the moles of the molecule. Stoichiometry, molecular weights, empirical formulas, atomic weights. So I have my ratio. I'm sorry, Cassidy?
Oh, I just said okay.
I have my molar ratio. Cassidy, which one do I divide by?
The atomic weight?
Nope. I've already done that.
Oh, sorry.
And
Divide by the moles of aluminum because it's the smaller number.
I divide by my moles of aluminum, and I get 1 mole of aluminum and 1.5 moles of oxygen. This is the ratio, 1 to 1.5. So I have to get rid of that half mole of oxygen. So I'm going to multiply that by 2. So I have 3 oxygens, 3 moles of oxygen in my mole of aluminum oxide. But you got to be careful, guys, because if you multiply 1 by 2, you have to multiply the other by 2, or else you change the ratio. If I didn't multiply the aluminum by 2 as well, I would have changed my ratio from 1 to 1.5 to 1 to 3. So you have to multiply both by 2, and I get 3 moles of oxygen, 2 moles of aluminum. The empirical formula is Al2O3. We good here, guys?
Yep.
Yeah.
The hardest part for empirical formula problems is finding the weights. Would you agree, guys? You've done these problems before. Isn't that the hardest part?
Yeah.
Yeah.
All right, so that's where the nuances come in. I have 0.2636 grams of nickel. I put that in a crucible and I heated it in air, which means that the air was contributing something to the nickel. In this case, I made nickel oxide. Okay? As a matter of fact, I made 0.3354 grams of nickel oxide. What is the empirical formula for the nickel oxide? I got one of my weights right off the bat, the 0.2636. Now you got to apply a little bit of logic. Am I saying there's anything in my nickel oxide except oxygen and nickel? Is there any other element? Am I implying there's any other element in there?
No.
So I've got my 0.3354 grams, which is composed of nickel plus oxygen weight. I have to realize that all of the nickel weight came from the initial amount of nickel. So to get the weight of the oxygen, all I have to do is take the whole weight, subtract the weight of the nickel. That will give me the weight of my oxygen. So once I get the weight of each, do the same thing we did before. Convert the weights to moles, divide by the smallest amount of moles, and then use a multiplier if necessary. So I subtract my two weights out. I get 0.0718 grams of oxygen. Divide them out. I get 0.004491 moles of nickel and 0.00449 moles of oxygen. I don't care. Which one do you want to call the smallest? Divide them both by the smallest. I get a 1-to-1 ratio. Therefore, my empirical formula is NiO. Questions here, guys? Any questions? All right. A sample was assayed to give 26.57% potassium, 35.36% chromium, and 38.07% oxygen. Now, guys, I know when you got this problem in intro for the first time, you freaked. It's like, how in the world do I figure this out? All you got to do is pick a number. Jasmina, what's your favorite number?
13.
15? Okay. So
13.
if you 13. If you have 13 grams of the compound that contains potassium, chromium, and oxygen, if you have 13 grams, then isn't 26.57% of that potassium's weight? Shake your head, Jasmine. I can't hear you.
I'm sorry, what did you say?
If you have 13 grams of the whole compound that contains potassium, chromium, and oxygen, if you have 13 grams of that, isn't 26.57% of that 13 the weight of the potassium?
Yes.
And isn't 35.36% of that 13 the weight of chromium?
Yes.
And isn't 38.07% of that the weight of oxygen?
Yes.
So I don't want to use 13. I want to be lazy. Dylan, what number would I choose?
100.
So if I choose 100, then isn't 26.57% of 100 potassium's contribution? So that gives me 26.57 grams of potassium, 35.36 grams of chromium, and 38.07 grams of oxygen. I now have my weights. I can take my weights and I can turn them into moles. I turn them into moles by dividing by the atomic weights. I get 0.6800 moles of potassium, same amount of chromium, and 2.379 moles of oxygen. Now, Cassidy, what do we do?
You divide by the smallest moles, so the 0.6800.
Divide them both, and I get a molar ratio of 1-to-1 to 3.5. Jessica, what am I going to do now? Can I have 3.5?
You divide by the smallest.
We've already done that, Jessica.
Oh, I see it now. Okay. Then that's when you look at that chart.
You look at the chart, okay? So what are you going to multiply oxygen by to get a whole number? You have 3.5. You have 3.5. What do you multiply that by to get a whole number, Jessica?
Yes.
What number?
3.
If I multiply 3.5 by 3, I get 10.5.
Okay.
Start smaller.
I don't know.
Okay, fair enough. Remember what I told you. Remember what I told you. If you get a fraction, start with 2. You multiply 3.5 by 2, you get 7. Is that a whole number, Jessica?
Yes.
So you're done. So you have to multiply each one of these by 2, and you get K2 Cr2O7. Or if you want to use Gavin's method, the fraction here is 0.5. Divide the 0.5 into 1, you get 2. That's the number you have to multiply by.
I don't know. I kind of get confused at that.
Okay.
You're supposed to, so when you get to this point, you're supposed to like look at that chart and then are you supposed to, if there's like a decimal, then you're supposed to pick the closest one to it?
Okay.
I always mess that part up.
Okay. The chart is this. If your number ends in 0.5, multiply by 2.
So did
Right.
you round that, the last one?
No, I didn't. No, we didn't round it. What we did was we took the 3.44 and we multiplied it by 2, and that gave us 7.
That's what I'm saying. The 3.499 isn't 0.5. That's what I'm saying. So you just round it 3.5.
Yes, exactly.
Okay.
Yeah, exactly.
Okay.
I'm sorry, I misunderstood what you were trying to say, Jessica.
No, that's fine. Thank you.
All right, if you want to, Jessica, using the chart is perfectly fine.
But you said it's safe to always just start by multiplying it by 2, and then if you
If the
get
two,
a whole number, then it's good.
yes, for example, if this number turned out to be 4.33, right? And you multiply that by 2, that would give you 8.66, correct, Jessica?
Okay, yeah.
It's not a whole number. So
Right.
then you go 4.33 times 3. This ends up being 13 for all practical purposes, 12.99, right?
So then you round it?
Yes. This is
I mean,
close enough.
can't you just round the 8.66, or is it just because?
That's too far away.
Okay.
That's
Okay.
too far away.
Okay.
It has to be reasonably close to the number. Okay?
Okay.
Fair enough, Jessica?
Yes, thank you.
Any other questions, guys, on this? Okay, now we're going to get into a little bit more of a problem. How many of you have problems when you were given combustion analysis, determining empirical formulas from it? Anybody?
Yep.
All right. It's a very, very simple process. Okay? Now, what they're really saying is, when I'm doing this, okay, what they're really saying is you got naphthalene, which is a hydrocarbon, plus oxygen. Who said they had problems with this? Is it Dylan?
Yeah.
Dylan, I got a hydrocarbon mixed with oxygen. What are my products?
It's going to be O2.
Nope. First of all, what kind of reaction is this? I have a hydrocarbon plus oxygen.
Combustion.
Combustion. What are the products of combustion reactions? I don't know. It's a perfectly good answer, Dylan.
It's going to be H2O and CO2, right?
There we go. Yes. Each and every time when I have a combustion reaction, I'm going to get this. Okay. Now, what they're saying when they give this problem, they're saying that you have reacted naphthalene with oxygen, and you got the amount of naphthalene you reacted gave you 8.80 grams of carbon dioxide and 1.44 grams of water. Would you agree with that? That's what the problem's saying, Dylan?
Yeah.
Now, Dylan, can you determine the percent composition of hydrogen within water?
Yes.
Can you detect the percent of carbon within carbon dioxide?
Yeah.
Are there any other sources of carbon?
No.
Are there any other sources of hydrogen?
No.
So once you get the percentage of hydrogen within water, you can multiply that by the grams of water, and that will give you the grams of hydrogen that were produced. Once you get the percentage of carbon within carbon dioxide, you can multiply that percentage by the grams of carbon dioxide. That will give you the amount of carbon you started with. I've got the weights now, Dylan. I have the weight of carbon and I have the weight of hydrogen. Once I have the weights, divide them by the atomic weights. That will give me the moles, and divide by the smaller. Does that make sense to you, Dylan?
Yeah.
So we are going to find, if I have CO2, there are 12 grams of carbon in 44 grams of CO2. The molecular weight of CO2 is 44. The atomic weight of carbon is 12. So I get 0.273, which is the mole fraction of carbon. Guys, you understand, when I'm doing here, when I'm just using the 0.273, yes, I could take it and multiply it by 100. But then when I go to convert it from percentage into the real number you can multiply it by, I'm going to have to divide it by 100. So instead of going through that business, use something called the mole fraction, which is just simply taking the amount of weight of your part and dividing it by the whole. That will give you the mole fraction. I'm just avoiding multiplying it by 100. So I have my mole fraction. I'm multiplying that by 8.80 grams. This means I have 2.40 grams of carbon. Similarly, with my water, I have 2 grams of hydrogen and 18 grams of water. This means my mole fraction of hydrogen in water is 0.111. I multiply that by 1.44. This gives me 0.160 grams of hydrogen. I simply divide those amount of grams by the atomic weights. I end up with 1.25 moles of carbon and 1 mole of hydrogen. Jessica.
Yes.
I multiply 1.25 by 2. What's my answer?
2.5.
Do I use 2?
I don't even know.
It's 2.5, close to a whole number.
Yeah.
2.5 is close to a whole number?
Yeah, normally you round 0.5 to a whole number.
Okay, Jessica, we have to get real close to a whole number. 0.5 is halfway between 2 and 3, right?
Yeah, but I guess when I was always taught rounding, 0.5 is always rounded to a whole number. So that's why I thought that.
Jessica, forget rounding here. We're not rounding.
Okay.
We're not rounding here. We are simply, okay, Jessica, do you have me for lab?
No.
Okay. Stay after class. I'll explain something else to you in a second, all right?
Okay, I'm not sure if I'm,
All right.
okay.
Jessica, right now, when I'm dealing with the main body of the formula, you don't round. Okay?
Okay.
So you multiply 2 by 1.25, 2.5. Is that near a whole number?
No.
All right. Multiply 3 by 1.25. You get 3.75. Is that close to a whole number?
No.
Multiply 4.
What's the closest, I guess, what are you looking for?
I'm looking
Like
for,
0.9, is 0.8 okay? Or is
I
it,
would say no for 0.8, 0.9, probably.
okay,
0.9, generally speaking, if you're at 0.9, if you keep on adding bigger and bigger numbers, it starts to get absurd. All right. You end up with chemical formulas like Fe43, S27. It gets to be absurd at some point. All right. So if you get to the point, Jessica, where you're not happy with it, then I would go back and check your math again, because you may have done a math error.
okay,
If you get beyond 5, Jessica, I would say that you've done a math error. Go back and recheck your answers, okay?
okay.
So I'm going to multiply both of these by 4. I get C5.
5.
I'm sorry, yeah, C5H4. So my empirical formula is C5H4. Now, if I tell you that my molecular weight of naphthalene is 128, what is the molecular formula? You got to go back. Do you remember how we turned the molecular formula into the empirical formula? Gavin, do you remember how we did that?
Sorry, could you repeat the question?
How do we turn the molecular formula into the empirical formula?
Didn't we simplify it so that its coefficients were minimal?
I have C6H12O6. That is the molecular formula. What is the empirical formula?
Shouldn't it be C3H03?
No, you're kind of, I think what's happening is you are.
I'm mixing up something with something else. That
Yeah,
12.
that's the formula.
I missed it.
That's the formula. What is the empirical formula?
Oh, so it should be CH2O.
How'd you get those? How did you get those subscripts?
I divided all the subscripts by 6, since 6 was the common
So
denominator.
if you divided to go from the molecular formula to the empirical formula, when you're going from the empirical formula to the molecular formula, what do you think you're going to have to do?
I multiply it by 6, since we'll be doing it from the
Yes.
empirical.
So you have to keep that in mind, guys. When you're going from the molecular to the empirical, you divide it by an integer. When you go from the empirical to the molecular, you're going to be multiplying by an integer. Okay? So right now I have C5H4. Okay? I don't know what my molecular formula is. So that's going to be CXHY. But I know when I am getting my molecular weight that the combination of CX's and HY's is going to add up to be 128. So if I look at my empirical formula, C5, 5 times 12 is 60. And 4 times 1 for the hydrogen. My empirical weight is 64. So I can compare the empirical weight to the molecular weight, and that will give me the number I have to multiply all the subscripts in the empirical formula by. I divide 128 by 64. The number I get is 2. So this means I have to multiply C 5 times 2, H 4 times 2. So I get my final formula as C10H8. Does that make sense to you all?
Yep.
So, formula-wise, okay, I have a compound with an empirical formula of CH2O, and that has a molecular weight of 180.19 grams. Our strategy is going to be, we're going to add up all the atomic weights, and we're going to get what the empirical weight of my empirical formula is. Then I am going to take the molecular weight, divide it by the empirical formula weight. That will give me the multiplier. I simply then take the multiplier and multiply it by each one of the subscripts in the empirical formula, and I have my molecular formula. So when I'm dealing with CH2O, I get 12 from carbon, 2 from hydrogen, and 16 from oxygen. So my empirical weight is 30. I divide the 180 by 30. This gets to be 6. I multiply my 1 carbon by 6 to give me 6 carbons, my 2 hydrogens by 6 to give me 12 hydrogen, and my 1 oxygen by 6 to give me 6 oxygens. Are we good, guys? Does this make sense to you?
Yep.
Okay. I have about 25 minutes left. All right. I will stay after to answer questions on the test. Okay. What I want to do right now is I want to get into some more complicated empirical formula problems. Can we see the screen I got up there?
Yep.
What is the mass percent of sulfate in aluminum sulfate? Somebody make a suggestion. How do we start this?
When the first thing you want to do is find the total mass of the molecule there.
I want to find the molecular weight, right? Then, Gavin, what am I going to do once I have the molecular weight?
Take the weight of the sulfates based off of how much sulfate there is, which in this instance there'll be 3 sulfates for the entire molecule.
That's
divided
important.
by the total weight.
That was important. What we're dealing with is the contribution of the entire sulfate. So whatever sulfate's ionic weight is, I'm going to have to multiply that by 3. So absolutely. Sulfur weighs 32. Ugh. Ew. Okay. I hope you followed along with my screwed up math there. Okay. So my sulfur weighs 32. I've got 4 oxygens. 4 oxygens are going to be 4 times 16, 64. My SO4 contribution is 96.06 times the 3 for a total of 288.18. So my total weight, I have 2 aluminums, which is 53.96. So this gives me a total weight of 342.14. My 288.18 divided by 342.14 gives me 83.74. Go 39% of sulfate. We're good, guys. Do we understand how we got that answer? Albeit it was wrongly calculated. Okay. The U.S. Food and Drug Administration recommends that an adult consume less than 2.4 grams of sodium per day. What mass of salt can you consume and still be within the guidelines? Legitimate problem, guys. This is actually is a real life problem. How are we going to, what's the strategy we're going to use? Can anybody make a suggestion?
Find the molecular weight of sodium chloride first.
Okay. Then what are we going to do once we find the molecular weight of sodium chloride?
Then you'll divide it just, oh wait, how can you consume this? Divide it just by the weight of sodium?
Yep, that will give me the percent of sodium within sodium chloride. Okay.
And then multiply that by 100?
Not quite, Cassidy.
Okay.
What I have, when I do that, that gives me the percent of sodium chloride within, it gives me the percent of sodium within sodium chloride, correct?
Yes.
So that isn't the percent of the mass that we want to find out. Percent of sodium within the mass of sodium chloride. Doesn't that have to be equal to 2.4?
Yes.
So basically, what I'm going to do is I am going to determine, as I said, I'm going to determine a percent of sodium from the formula. I do that math out, I get 39.33%. Now, isn't 39.33% of the weight of sodium chloride equal to 2.4 grams? I'm waiting for a yes.
Yes.
So I take the 2.4 and okay, I did it by a different method. Sorry, I didn't see this. If my percent of sodium is 39.33%, doesn't that mean if I have 100 grams, 39.33% of it is sodium?
Yes.
So if I do this by a dimensional analysis portion, if I have 2.4 grams of sodium, if I multiply that by my 100 grams of sodium chloride, in that are 39.33 grams of sodium. The grams of sodium cancels. This gives me my weight of sodium chloride. Or if you want to do it by doing the percentage, 39.33% of my sodium chloride weight is equal to 2.4. 0.3933 times X is equal to 2.4. 2.4 divided by 0.3933 is equal to 6.2 grams. Both of them are similar math problems. It's just a matter of how you want to go about the final solution.
Okay.
Questions on this? Are we okay? Are we okay with this, guys?
Yes.
New problem. 5.82 gram silver coin. Remember, coins are alloys. They are not pure metals. Is dissolved in nitric acid. When I add sodium chloride to the solution, all the silver is precipitated as silver chloride. The precipitate weighs 7.20 grams. How much silver is in the coin? Can anybody offer me a solution? Again, a real life practical problem. All right, riddle me this. Has all the silver been converted to silver chloride?
Yes.
So if I had a way to figure out my percentage of silver in the silver chloride, then couldn't I get the total weight of silver?
Yes.
How am I going to do that, Cassidy?
You're gonna find the percent of the silver in the chloride, so find the mass of that, and then divide it by the mass of the silver.
Okay. Tell me what numbers I'm going to do. Give me numbers here.
I don't know honestly if you'd use the 7.20 or the 5.82.
Okay. For the 5.82, what's that the weight of?
The silver coin.
So do I know the percentage of silver in the silver coin?
Yes.
You do?
Oh, no, I guess not.
That's
no.
what we're trying to find out, isn't it?
Yes.
Okay, so am I going to use the 5.82?
Yes. No, I'm sorry.
Okay, have some more coffee, Cassidy.
I'm just
Cassidy.
trying to participate.
All right, let's look at the problem. The final thing it's asking you is to determine the percentage of silver in the coin. If you knew the amount of silver in there, you'd be able to just divide the part by the whole, right?
Yeah.
So do we know the amount of silver?
No.
But we do know that all of the silver was converted to what?
Silver chloride?
Silver chloride. Can I determine the percentage of silver within the silver chloride?
Yes.
Can I then apply that percentage to the weight of the silver chloride to get the weight of the silver?
Yes.
Once I get the weight of the silver, can I determine the percentage of silver in my coin?
Yes.
That's what we're going to do. First thing we're going to do, when you're getting a problem like this, you got to wade through the crap. You don't care it was dissolved in nitric acid. What you care about is that it made silver chloride. You don't even care that they used sodium chloride to do the precipitate. What you need to know is that all the silver was precipitated as silver chloride and that that precipitate weighed 7.20 grams. So what we're going to do is We know that silver weighs 107.87 and that silver chloride weighs 143.32. Therefore, my percentage of silver in silver chloride is the 107.87 divided by 143.32. This gives me 75.265% silver. I know that the silver chloride weighed 7.20 grams. So I take the 75.265% of the entire weight, 7.20. This gives me the weight of my silver. Then from there, it's a simple matter of taking the grams of silver divided by the weight of the coin. This gives me 93.1% silver.
Okay, sorry. Word problems, I'm not fully there this morning, and word problems really kind of trip me up sometimes, so.
No, Cassidy, it's just, that's what I'm trying to do. I'm trying to get you to look at the problem and be able to develop a strategy for solving it.
Yeah, that
Okay?
definitely helped. Thank you.
New problem. A piece of plumbing solder. Solder is a metal containing lead and tin. Weighed 3 grams. That solder was dissolved in nitric acid and then treated with sulfuric acid. This precipitated the lead as lead sulfate, which after washing and drying weighed 2.93 grams. Okay, the lead has been taken out. It precipitated as lead sulfate. The liquid above the lead sulfate, that contained the tin. Okay, I neutralized it to precipitate out stannic acid, which I then heated, and the heating revealed 1.27 grams of tin 4 oxide. What is the analysis of the solder as percent lead and percent tin? Remember the way we just solved the last problem. Gabe.
Yeah.
You there, Gabe?
Yeah, I'm here.
Okay. What was the lead turned into?
It turned into lead sulfate.
Lead sulfate. Okay, do we know how much lead sulfate?
2.93 grams.
Can we determine the percentage of lead within lead sulfate?
Yes, you can.
Can we then apply that percentage to the total weight of lead sulfate to get the weight of lead?
Yes.
All right, tell me what to do.
So it'd be, once you get the molecular, mass of lead.
Okay, the atomic mass of lead, then what are you going to do?
Wouldn't you divide it by 2.93?
No. Nope, Gabe. I need to find the percentage of lead in the lead sulfate. How do I get that percentage?
Oh, you divide it by 2.93 times 100?
Nope.
Or no, that's empirical formula, right? I don't know.
I don't know is a perfectly good answer. Anybody have a suggestion for us? Remember, guys, how do we get in the last problem, how do we get the percentage of silver in the silver chloride? Gavin, you're itching to answer this.
When you take the mass of the lead in comparison to the mass of the entire lead sulfate?
Exactly. If you do that, that will give you the percentage of lead. Then what do we do?
That's where I have the problem is after that is once I get the percentage, I don't know what to do with it. I think multiply by 100. And then.
Okay, this is where we're at.
Okay.
We've got the lead, and the lead sulfate gives you a mole fraction of 0.68325. Fair enough? Gavin? Or 68.324%.
All right.
That's the percentage of lead within lead sulfate. Do I know the weight of my lead sulfate, Gavin?
Yes.
So if I know the weight of my lead sulfate and I know the percentage of lead in lead sulfate,
You can just multiply it by the weight.
multiply it by the weight. I multiply my mole fraction by the weight of my lead sulfate. This gives me 2 grams of lead. Are you following? Is everybody following me?
Yes, I am.
Okay. Now, if we look at the problem, we have 3 grams of my solder. Solder is only of lead and tin. Do I know how much tin I have in there?
Well, if it's properly made, then it should only have 1 gram of tin.
Should probably have only 1 gram of tin. By the way, to get the amount of my solder, my tin weighed, or my lead weighed 2 grams, my solder weighed 3, divide 2 by 3, I get 66.7. So correspondingly, if it's only made of tin and lead, my tin percentage should be 33.3%. Should be. But you're not certain that the solder had only lead and tin in it. If you solve for the tin percentage, you can check your result. Now, we created SnO2. The tin weighs 118.69. SnO2 weighs 150.69. So just like we did with the lead in the lead sulfate, we're determining the amount of tin in the tin oxide. That percentage is 0.78764. I multiply my 0.78764 by my total weight of tin. This gives me 1 gram of tin. I multiply the 0.78764 by the grams of my tin oxide. This gives me 1 gram of tin, which means that it's going to be 33.33%. Note, if I told you this solder originally weighed 3.5 grams, then you know that it wasn't composed completely of lead and tin, because 2 plus 1 equals 3. It's not the entire weight of the solder then. A strip of electrically pure copper weighing 3.178 grams is heated in oxygen until it's converted to the black oxide. Guys, if I refer to something as the oxide, that means that it has been combined with the metal to make the metal oxide. That's what saying it's the black oxide means. The resultant black powder weighs 3.978 grams. What is the percent composition and what is the empirical formula of the compound? Somebody make a suggestion. We got 3 minutes left, guys. Three minutes left, guys.
Are we assuming that it's copper too?
No, you're not assuming. You're trying to find that out.
Okay, so that's what we're trying to figure. Okay.
What's the oxide consist of?
Copper and oxygen.
And if I know what the weight of the copper is, how do I get the weight of the oxygen?
It would be the difference.
Okay, ladies and gentlemen, did you see that? If I have an oxide, the oxide is consisting of only the copper and the oxygen, because that's what an oxide is. So if I have the weight of the oxide and I have the weight of the copper, all I got to do is subtract the two of them. That will give me the weight of the oxygen. So I have Sorry, there's the slide. I have my weight of the oxide minus the weight of the copper. This gives me the weight of oxygen. Now I have the weights. Once I have the weights, it's a matter of converting to moles, then dividing by the smallest amount. If I want the percent composition, I take the percent copper divided by the oxide. This gives me 79.89. I take the weight of of oxygen, divide by the weight of the oxide. This gives me the percentage of oxygen. I have to convert by moles. I do the first one out. I got 0.0500 moles of copper. I have 0.0500 moles of oxygen. Now, Gavin, is it copper 1 or copper 2?
It would be copper 2 since you'd have the same moles of copper as oxygen.
Same moles of copper and oxygen. This means my formula is CuO. If my formula is CuO, then I know that my charge of my copper is a +2. I would look this last problem. I'm not going to get a chance to go through that unless you want to stay over. Do you want to stay over? This is your choice.
I have a test in 10 minutes for math.
Sorry, Gabe.
All right.
I have it pretty well explained. I've gone through these things step by step. It's your choice, guys.
You have to go, but thank you. I'll watch the recording later.
Look at the problem. I think this is the last problem.
Is this slideshow on my courses?
Yes, it is. This one, I believe it is. If not, I will upload it. Okay, Dylan?
All right, thank you.
Okay, guys. This is 10:45. Anybody have questions about the test? I consider this to be free time.
Are we going to be able to take the test at any time on Tuesday, or is that at like a scheduled time?
The test will be open from, I consider the normal time of the class to be 5:30 to 6:45. Okay, Cassidy?
Okay.
So I will open the test at 8 a.m. I will close it at 7 o'clock.
Okay, thank you.
Now, keep that in mind that there's a limit of an hour and a half for the test. So
Okay.
if you want to hold off and do it at the last minute, the last time you can start the test is at 5:30.
All right, thank you.
Anything else, guys? I believe I have a practice test. I am not certain whether I have I believe I have a practice test in here. I'm not entirely certain whether I have an answer sheet or not. Do not trust the answer sheet. I make answer sheets. I don't have it. I don't have one. Amazingly enough. Okay, I will try and upload a practice test for you. Okay, I just apparently didn't load it up yet.
Yeah, that would be awesome. Thank you.
Okay, remember, part of what I'm trying to do in chemistry, I want you to apply to other classes. And one of the lessons I've tried to tell you is if an instructor spends a whole lot of time on something, then you pretty well be assured that that's going to be on the test. I spent one whole period on empirical formulas. What are the chances there's going to be at least one empirical formula problem on the test?
Pretty high.
Okay. When you're going through and analyzing what you need to study for a test, look back and see, ask yourself, what did he spend a lot of time on? I spent a lot of time, I believe, on getting the atom straight in terms of number of electrons, number of protons and neutrons. believe I spent a lot of time on that. I spent some time on chem and physical changes. You should know that. Dimensional analysis I spent some time on. Lots of time on subatomic particles. Now let's go on this. This is better. Guys, look at the online outlines. That will tell you. That will tell you what I covered in each one. I went through atomic structure, the history. Guys, somewhere, somehow, have a printed copy somewhere of these guys and what they did. I went through the structure of the atom. How a single problem. How do you get the average atomic mass? I also went through periodic trends. Be familiar with the periodic trends and be able to rank them from highest to lowest or lowest to highest. What the different areas of the periodic table encompass. How to determine valence electrons. Questions, guys, on the second, basically second chapter.
I have a question on the test.
Sure.
If we have a printed textbook, can we keep that in front of us?
Yes.
All right, thank you.
Yes, you may. You are not allowed to use a browser, any browsers. So if you have a online text, I'm sorry, I'm not letting you use it because I have to prevent it. I will also upload a practice honor lock exam. If the practice honor lock is just to get you familiar with honor lock and the nuances to taking tests in that. The first part of this, I talked about matter. Matter, sig figs, guys. Definitely no sig figs. Chem and physical properties, be able to do that. Know how to balance chemicals. Definitely, guys, know how to name them. Definitely know how to name chemicals. Chemical reactions. Be able to recognize what type of reaction it is. Once you know the type of reaction, be able to predict the products. Once you are able to predict the products, tell me whether the reaction goes or not. Once you know the reaction goes and you have balanced all the chemicals themselves, then I want you to be able to balance the chemical reaction. And I think that's where we left off in terms of being able to calculate molecular weights and what we went through today. You are not responsible for stoichiometry. Stoichiometry is where we're going to begin the next. You are not responsible for stoichiometry. That's where we're going to begin the next test. Show your work. I cannot emphasize that enough. If you do not show work, you do not get credit. Don't pay attention to the email I'm going to send in a few minutes. Okay? Unless you need to inform me that you have a extra time or something like that. If most of the questions are multiple choice, true, false, there are problems on it. If it is a problem, then if it's a text box that you need to put something in, I need you to show work. I need you to show work so that I can give you partial credit. If you get the right answer, nah, I'm not going to do that. No. You have to show work. If you don't show work, then that means you don't get any credit. Fair enough, guys? Type it in the text box just like you do for the lab. Cassidy, a question?
No, I was just responding. Yes, I don't have any other questions.
Understand, the more work you show, the more chance you're going to get points from it. If you throw more spaghetti on the wall, there's a chance that the spaghetti is going to stick on the wall. So the more work you show, the better off you'll be. And the clearer you are, the better chance you'll get points from that. Can I answer anything else, guys?
I personally don't have any other questions, so thank you very much.
Okay, Jessica, I want you to stick around for a second, okay? Jessica?
She's already left.
Bye. Okay, I guess I'm not going to be able to explain that to her then. Yeah, it's nothing major. It's just something that gets to be confusing in the next lab you're doing, not the hydrate lab, but the empirical formula lab. It's a little bit confusing how that gets, one of the answers gets rounded and the other one, you have to use the multiplying number. And those of you that have me, I'll explain that then. Okay, guys, if that's it, take care. I will see you on the next time I see you.
Have a good weekend. Thank you.
You too.
See ya.
Take care.
Thank you.
Take care, guys. Test on Tuesday.